Hello, I'm Mr. Franklin. Today we're going to be talking about energy. But before we begin, if you want to follow along, there's a document in the uh, comments down below, or it's in our Google Classroom for those of you following along in my class. So last time we talked about work. So today we're going to talk about energy. And energy at a basic level is the ability to do work. So ability to do work is energy. Another way to look at that is to substitute the definition for work, because work is a force applied over a distance. So if we substitute that in for our definition of energy, we would get a definition that says energy is the ability to apply a force or create a force over a distance in the future. So the ability to apply a force over a distance in the future is energy. So before we get into what that visual of what that translates into, what are some types of energy that we're familiar with? Just throw out some in your brain, write some on your pause it, write some in your notes. So let's think. Um, Electrical energy. We can think of that. Electrical energy. Some of us might say light energy. I've heard that. Um, in one class, I had someone say wind energy. Let's see, radiation. So some of these, it's not going to be apparent right off the bat that these types of energy fit with our current definition. But I think as we explore some, we're going to find out some more. So what we're really going to be talking about for the most part is mechanical energy. Okay? Which wind energy is actually a type of mechanical energy, or can be. So there's all kinds of different ways energy can be transmitted, which is what electrical, light, and wind really have to deal with. But in the end, they all, at some level, have the ability to apply a force over a distance, which is energy. But today we're going to focus on one in particular, gravitational potential energy. So this type of energy is the energy an object has, so the energy an object has based on its height above the ground. So let's take a look. If I hold an object above the ground, as soon as I let go, it's going to fall, right? So energy is the ability to create a force over a distance. Before I let it go, has it moved? Has there been a force? Not yet. So it has the potential to move, but as soon as I let go, the object is going to fall. And when it's falling, we actually lose our potential energy because the object is actually going through the process of work, force times distance, okay? But before it's dropped, it has potential to drop. So this energy of an object based on its height above the ground. So the higher we drop an object from, the higher the potential energy is going to be. And that should also make sense. So the symbol for gravitational potential energy is the letter U. The unit, notice this, the unit is going to still be the joule. And what we're going to find out is work and energy are basically two sides of the same coin. So while a force is being applied over a distance, we have work. If it has the ability to create a force over a distance, it's going to be energy. And because they're really two sides of the same coin, we're going to see that their unit is the same. It is the joule. The equation for potential energy is U equals mass times the acceleration due to Earth's gravity times the height of the object, mgh. U equals mgh. So if we go back to the picture I was drawing, mass times gravity times height, Notice, does the mass of the object in this case change as I change its heights? Height 1, height 2, height 3. No. Does the acceleration due to Earth's gravity change? No, it's the same throughout. So the only thing that changes is the height. So the greater the height, the greater the potential energy. The less high it is above the ground, the lower the potential energy. Okay? So let's take a look at our first example problem. Calculating potential energy. We have our egg, which we said when we looked it up for our egg drop experiment that it has a mass of approximately 0.07 kilograms, and we're going to drop it from a 5-meter height, which is where the railing was of our balcony. And we're going to drop it. What is the potential energy of the egg? So I do my KUF, known. So don't mix these up as we get into energy. We're going to use some letters here. Known, unknown. Okay, that does not mean potential. This U is unknown, this U is potential energy, and this is for formula. Okay, it's been a while, so let's just make sure we're clear. Known, unknown formula. So we list them. Mass equals 0.07 kilograms. Distance equals 5 meters. And my acceleration, they don't give it in the word problem, but because we're dropping it, the acceleration has to be negative 9.8 meters per second squared. And technically, it's also going to drop a negative 5 meters because it's going to drop this. Now, we plug this in. We write our formula, U equals mgh. So mass is 0.07 kilograms times the negative 5 meters. Actually, I'm going out of order here. Let me fix that. Times negative 9.8 meters per second squared times the negative 5 meters. We plug all of those in, and let's see. I'm going to do them step by step. So we got 40, 45, that's 49. Okay. And times 0.07. 7 times 9 is 63. Carry the 6. 28, 34. Okay. And I've got 2 decimal places. 1, 2. So 3.43 joules. Did I do that right? Yes, I did. 3.43 joules is the amount of potential energy before it drops. Now I want you to notice that once we actually let it go, it will do work of the same value. Okay? But for now, and here's the other hint, mass times gravity is the force due to weight. Height is the distance it's going to travel. So before it drops, mgh, potential energy. After it drops, force times distance, which the force in this case is the weight, which is mg. So we're going to notice that work is done while it's dropping, and potential energy is the potential it has to do that work. Okay? All right. So you have some practice problems. So go ahead and try those, and then we'll come back and do another, take another look. Okay. So now that you've come back, let's take another look at this. When I drop the egg, it has potential energy right up here at the top before I drop it. But what about right before it hits? It's falling and falling, and right before it hits, so everywhere along its fall, it has potential energy. Some of it's converted into work, but each spot we could actually calculate its potential energy. But right before it hits the ground, just in that split second before it hits the ground where its height is practically zero, what's its potential energy? Well, if mass times gravity times height, if my height is zero, then what's my potential energy? It's going to be zero. So, one of the great uses of potential energy, and this is actually how we found the height of the railing to be 5 meters, was we actually worked it backwards. We know that we have an egg, or we have a box. This time it's 10 kilograms, and it does 100 joules of, it's going to have 100 joules of potential energy, or it could have been 100 joules of work if we could measure that. We want to know what's this height or what's this distance. So the mass is 10 kilograms. Acceleration due to gravity is negative 9.8 meters per second squared, and the potential energy is 100 joules. My unknown, I'm looking for distance, which is the same thing as height. We could use the letter H. Okay, so U is 100 joules equals 10 kilograms. G is negative 9.8 meters per second squared. I'm running out of room here. And my height, which I don't know, H. Okay, so I'm going to move it over here so we can see 100 joules equals 10 kilograms times negative 9.8 times height. And that's meters per second squared. So first I'm going to do my first step here. I'm going to multiply these two numbers, which means this is negative 98 times my height. Then I'm going to divide both sides by negative 98. I don't know where that extra negative came from. I'm trying to write fast, I guess. But we do that on both sides, 98 and 98. Okay. We divide that, and 100 divided by 98 will be slightly bigger than 1. So 100 divide 98 in my calculator equals 1.02. So my height equals negative 1.02 meters. And does that make sense? It's negative because we're starting from up here and it's falling in a negative direction. Okay? Negative 1.02 meters is the height. Now the actual height, if we were to measure it from the ground, would be a positive 1.02. Okay? So you have some practice problems on those, so try those. Here's another practice problem. It's pretty much the same problem, except now we're going to be looking for the force. So we're going to drop a box 2 meters with the potential energy of 100 joules, and we're looking for what is the force that is causing the box to move. In other words, what is its weight? What is the weight of the box? That's another fancy way of asking this question, because it's the force due to gravity. So our distance is 2 meters, our potential energy is 100 joules. We're looking for force, so U equals mgh. We know mg is the force, so we could put the force here. What's the height? The height is 2 meters. Divide that by 2, and we get F equals 50 newtons. So we know our box weighed 50 newtons. I could continue to divide that by negative 9.8. I could go force equals ma, and the force is 50 newtons. And my mass, I don't know, but my acceleration is 9.8. Divide both sides by 9.8, and you can find your mass. And in this case, my mass is going to be 50 divide 9.8, which is 5.10 kilograms. Okay, that's part B of the problem. You also have some like this, so go ahead and try those. Okay, we've already talked about this, but let me just recap. The potential energy is mgh, and it is before the drop. The work done would be force times distance, which is also mgh, because the force due to gravity is the weight. Let's not confuse that with division here. Force times distance, which is mgh. It's the same equation basically, but this is after the drop or after the release. Okay? It's a subtle difference, but it can actually be very important as we get into some other things. Okay? So before it is potential energy, after it is work.